Alright, so here in this video, I will just kind of go through a few multiple choice questions for you, just to show you how to attack some of these problems, okay? So here in the first one, we have a block that is at rest. It is being tugged by some force here to the right, that's called T, and the diagram gives us an opposing force F here pointing to the left, and essentially it asks us what force of static friction is required to keep the block in equilibrium. So you want to find this force of static friction that is keeping this system stationary, so it's not moving at all. Okay, so the first thing I suggest you do is break this particular force T into its component. So I'm going to go ahead and call this Tx, and Tx in this particular diagram is just T cosine of 60 because Tx here is your adjacent to this angle given. The angle given here is touching the horizontal axis, or aka the x-axis in this case, so that would just be cosine. So T is given as 40, so if you do 40 times cosine of 60, that'll just be 20 newtons. Okay. All right. Other than that, F here is given as 17.5, and we're trying to find again the force of static that is required to keep this stuff stationary. So at this point, if you can't come up to the answer yet, then I would say you're thinking too hard. So here, Tx here is 20 to the right. F here is 17.5 to the left. In order to keep stuff stationary, you need equal and opposite forces. So in this case, my instinct would tell me this is choice A because you need an additional 2.5 pointing left. Okay, so if you need to, watch my arrows that comes up here. This is 20 newtons already, right? So Tx here is 20 newtons. Well, it gives you F, which is already 17.5, right? The system's not moving, so once again, all your vectors pointing to the right must equal to all your vectors pointing to the left. So the fact that this is already 17.5 suggests that the additional force needed is 2.5, but pointing in the opposite direction. In this case, it would be pointing left. So without thinking too hard, the answer would just be A. It'd be negative 2.5 in the I direction, which is in the X direction, newtons. Okay, so that's that for the first one. The second one here is this here a box of mass M on a rough inclined surface. And then the force here in the diagram is being pulled at some angle phi here, or phi, however you want to say it, above the inclined surface. And it essentially wants us to find the magnitude of the net force acting on the box, which is not bad, right? It's just looking for the net force. So all we have to do is identify all of our forces along the surface of the incline. All right, so I'm going to go ahead and draw my f of g out here. This is my f of g vector. For inclined surfaces, we typically take the surface of the incline to be our x-axis, and then perpendicular to that would be our y-axis. In this case, we don't really need to touch our y-axis because our net force in the y direction is going to be 0 because the surface, or excuse me, the block here is to remain on the incline. So therefore, it does not accelerate off the inclined surface. So net force in the y direction is going to be 0. So therefore, the only thing we really need to focus on is net force in the x direction. So the box either gets accelerated up slope or down slope, or it'll move at a constant rate. Okay. So the point here is that you don't need to worry about the net force in the y direction because for inclined surfaces, the net force in the y direction will be 0, assuming the object remains on the surface incline the entire time. All right. So here's my f of g. I want to break it into its component. This is f of g y, and this is f of g x. Right. So f of g x is going to be mg sine theta. The angle of the incline will be the same as this angle here. Okay. So here, if you look at f of gx, this is your opposite. So because this is opposite, it needs to be sine of theta because sine is opposite. Okay. Other than that, f of gy is going to be mg cosine theta. But as I stated earlier, the fact that this particular question is asking for the magnitude of the net force acting on the box suggests that you need to just focus in the x direction. So why I label f of gy for you, you don't really need to use it. Just because it's there, you don't need to touch it. Okay, so just focus your attention in the x direction because the box here is going to slide up or down the incline. All right, other than that, I'm just going to go ahead and draw the other component of f. So you notice here f is a diagonal applied force relative to the surface of the incline, right? Because it is a diagonal, it will have components. So here I just drew out f of x here. This is f of x because it is along the surface of the incline, which we once again take to be the x-axis. So I'm just going to say that fx here is just f, whatever the hypotenuse is, which is the vector itself, times cosine of the angle. Okay. Well, it's cosine because this is your adjacent relative to this particular applied force. All right. As I said earlier, I don't need to focus in the y direction. So for f here, I'm not even gonna write fy out because I don't need it. The other thing that we need to do, draw out, is that the fact that it says a rough surface, and it says that the magnitude of the frictional force here is little f. So here, if the box is being pulled up slope, f of k, or f of friction, needs to point against it, aka down slope, for this particular diagram. Okay, so I'm just gonna call that f down there, and this f here is the force of friction, and it is going to point against the block's motion. So if you're pulling the block up the incline, f of friction needs to point down the incline. All right, so as you can see here, all you have to do really is just identify the forces that's in the x direction or along the surface of the incline. So here I'm just going to enlarge it for you. Here I have f of x pulling the system up slope, but acting against it, I have f of gx. I also have f of friction. Okay, so just by looking at these three enlarged, components and vectors here, I'm just gonna go with choice C. Choice C says f cosine of phi, or phi, however you want to say it, minus f of gx, which is mt sine of theta, minus friction. So choice C is the only answer that matches with my vector and vector components in the x direction along the surface of the incline. So I'm just going to highlight that as my answer. Alright, let's do this one. This one here is just a 9 kilogram block shown below is at rest, and it wants us to find this particular angle that touches the ceiling. Alright, so to do this one, it's pretty light work. Alright, it really is just a geometry problem. To find an angle, you need to have two sides, right? So the information here that's given is pretty useful. You just have to make sure you can maximize it. The mass of the block is 9 kilogram. So I'm just going to go ahead and find the weight of the block. The weight of the block here, pointing down the screen or down the page here, is just going to be f of g equals mass times gravity. And here it says use g as negative 10 meters per second square. So I'll use that, okay? So to find f of g, I'm just going to plug the mass in, which is giving us 9 kilograms. G here, I'm just going to use negative 10 because it said to use so. And therefore, 9 times negative 10 is just negative 90 newtons. Well, if the system is at rest, it suggests that it's in equilibrium. For objects to stay in equilibrium, your forces in the x direction must cancel. Your force in the y direction must also cancel. Hence, the net force for the system is 0. Alright, so to do that, here's my vector for this string along this slope here, or along this, well, I guess just along this rope here. This is pointing towards the ceiling. Therefore, this is going to be my tx, okay? That's going to be my ty. So here are my variables. That's t, this is tx, but tx here is just 45 because, well, the 9 kilogram block is not moving left or right. So the fact that the diagram gives you a 45 newtons pointing leftward suggests that the vector pointing right, in this case tx, must have the same magnitude. So it must be also 45, okay? Now, there's one component pointing up, this is ty, but ty here is just 90 newtons. Why? Because in this free body diagram, there's only one force pulling down on the two string, and then there's the weight of the box itself. Well, we already calculated the weight of the box, which is negative 90. Well, in order for this box not to be, swinging downward or being lifted up, the forces in the y direction must equal to 0. So therefore, if this is negative 90, common sense tells you that ty must also equal 90. Okay, again, equal in magnitude, just opposite in direction. So one is negative 90, one is positive 90. Now, once you know that, at this point, you can move theta down here because theta that's touching here, the horizontal axis, should also be the same as this theta where my cursor is tracing. But I'll keep theta in the diagram. I'm just going to move my vector components, okay? When it comes to vector components, you can cut it and shift it. As long as you don't tilt it, the arrow stays the same. So I'm going to move my ty over there, that's 90. Well, I'm going to move my tx up here. So you notice I'm just moving my components. I'm not tilting the arrow. That's okay to do. All right, so that's 45. Well, why did I move that? That's so I can make this triangle. Well, here's theta. This is my opposite. That's my adjacent, right? So therefore, to find theta, I'm just going to use tangent. Well, I'm using tangent because I have my opposite and I have my adjacent. So tangent is opposite over adjacent, aka ty over tx in this case, because ty is my opposite, tx is my adjacent. So to find theta, I'm just going to arctan it. Therefore, all you have to do is really plug and chug now, right? So which is ty, which is 90, and then tx, which is 45. So I'm going to do 90 divided by 45. Make sure your calculus is in degree mode. And if you do that correctly, you should get an answer of 63.4, which matches choice D. Okay. All right, let's do the next one. Here in this one's a little more challenging. Here you have a 42 kilogram object suspended. It's got really 3 ropes here. Yeah, it says 2 cables, but if you want, you count this as T1 and T2, vice versa, and T3. Let's do it. So here it asks you to find the magnitude of the tension in the cable to the wall. So here's the wall. So this is really the cable that we're trying to find. So the diagram didn't give us any sort of notation. So when it doesn't, feel free to dictate it yourself. Okay. So I'm just gonna go ahead and find my f of g. I like to find my f of g first just because I know it's there. So f of g here, that's just pointing down the page. Here in blue, I'm just gonna call this particular vector T1. Once again, you can call it whatever T you want. I'm just gonna go T1 on my work. And then the other vector that is important because it says 2 cables here, and that I'm just gonna call T2. And once again, if you want, you can call the segment where my cursor is going back and forth T3. But there's really no need here because T3 is really just your f of g, okay? So that's entirely up to you if you want to introduce more tensions in your system, or just understand that really T3 here will be the same as f of g. All right, so I'm just going to bypass that for this particular problem. Other than that, let's go ahead and do it. So ultimately, we're trying to find T1, all right, the tension that touches the wall, which is T1 in my work. So let's go ahead and set up our information. Here, T1 is a diagonal, so it has to have a Tx. Tx in this case would be T1 sine of 75. Once again, it's important that you pay attention to where the angle is placed. In this particular diagram, 75 degree here is placed touching the vertical axis. So opposite of that would be sine. Okay, so make sure you do your sine and cosine correctly. Don't just memorize stuff. Here, my T1x is T1 sine of 75 because this component is opposite of this angle that's given to me in the diagram. Now, likewise with T1y. T1y is cosine because this leg is my adjacent relative to this angle, okay? So all you have to do is make sure you apply adjacent and opposite correctly, and whether that's cosine or sine, that depends on the diagram and where the angle is given to you. Okay, so T1 is that. And then T1x is T1 sine of 75, and then T1y is T1 cosine of 75. And then I want to do the same thing for T2. T2 is a diagonal, so it has to have components. So T2x here is going to be just T2 cosine of 57. If you kept up with the previous problem, this angle that's given up here is the same as this angle down here. Okay, just because you're really just bisecting 2 parallel lines. Okay. All right, other than that, let's go ahead and do T2y. T2y in this particular case, if this is 57 degrees, T2y is your opposite, and opposite would suggest sine. So T2y would just be T2 sine of 57 degrees. And all we have to do here is just set up our forces in the y direction, x direction, or x and y, however, whichever you want to do first, it's up to you. I'll just go ahead and do x first. Okay, I'm just going to set this properly up for you. Again, the system is in equilibrium, so there's no acceleration. So if you look at this particular diagram, you have an arrow pointing right, which is T2x. You have an arrow pointing left, which is T1x. So if you take T2x minus T1x, it must equal to 0 because the system is not accelerating. So I made a statement. I said T2x, which is the one pointing right, subtract T1x, which is the one pointing left, that must equal to 0. So here I can just isolate for T2x by moving the negative T1x to the right side, which changes sign. So it's a minus on this side, but when you move to the right side, it becomes positive. So as you can see here, I have T2x is equal to T1x, which again makes sense to me, right? The system's not moving, so there are only 2 arrows in the x direction. So the one pointing right must equal to the one pointing left. Now, ultimately though, we're not asked to find neither one of these. We're asked to find T1. So to find T1, I need to get rid of T2, okay? So I'm just gonna expand this, T2x. In my work, in my diagram here, T2x is T2 cosine of 57 degrees, and I just made a substitution. T1x though is up here, which is T1 sine of 75 because the angle once again is given touching the vertical axis here. Okay, I need to get rid of T2. I want to keep T1 because that's what I'm trying to find. So in this work here, I'm actually going to isolate for T2 because I need to get rid of it. Okay, so to get T2 by itself, algebraically, I just need to divide both sides by cosine of 57 degrees. So really here in my work, it would just be T1 sine of 75 divided by cosine of 57. Now, if you punch this in your calculator, sine of 75 divided by cosine of 57 degrees, you'll get about 1.774 T1, right? So really sine of 75 and cosine of 57 it's just some number, and you can reduce that to just get a coefficient in front of T1, and that's what I did. Okay, so I can make the statement T2 is 1.774 times T1. Well, I'm not done yet. I have two unknowns here. I have a T2 and a T1. Okay, so I can just go ahead and set up my information in the y direction now, just so I can get rid of another, or I can get rid of T2. So I start with the same statement here. Net force in the y direction is equal to 0, right? I enlarge this arrow for you because all you have to do is make sure you draw your arrow or arrow components or vector components correctly. T2y that I enlarge here is pointing upward, right? T1y that I enlarge is pointing downward. In addition to that, though, f of g is also pointing downward. So if you look at this particular schematic, you have one arrow pointing up, which is just T2y. You have two arrows pointing downward, right? So I would just say up equals down. So in this case, I'm just going to say T2y, which is the arrow pointing up, subtract it, from T1y and f of g. So T2y minus T1y minus, addition to that, f of g must equal to 0. I hope that makes sense, right? I do up minus everything opposing it. In this case, there's only one arrow up, so that's the only term. There are two arrows down, so I subtract both those arrows. Here, I'm just going to go ahead and isolate for T2y because I have a statement on the left side using the x information here that I have T2 by itself already. So here on my work on the right side, I'm going to isolate for T2y because I can get rid of T2. So I'm just going to move the f of g that's negative and the T1y that's negative to the right side of the equation by adding both of those. So both of these terms now becomes positive once you move to the right side. I want to expand T2y. So T2y here is just T2 sine of 57. Once again, up in my work here, T2y, based on the angle given, is T2 sine of 57. That's what I did. And then T1y is the same. T1y over here is just T1 cosine of 75 degrees. That's what I did there. And then f of g is just f of g. Okay. So if you punch in sine of 57 on your calculator in degree mode, you get 0.839. Likewise, with cosine of 75, you punch in cosine of 75, you get about 0.259. And then f of g here is just mass times gravity. Here I just did 42 times 9.8, and that is 411.6. Keep in mind when you do this f of g, use g as 9.8 because the negative sign has already been introduced in my second line of work here. Okay, so don't plug in another negative. All right. Other than that, I'm just gonna go ahead and substitute out for T2. Ultimately, again, I'm trying to find T1, so I need to keep T1 in my work. I don't know what T2 is, but from the X information, I know that T2 is roughly 1.774 T1. So I'm just going to get rid of T2 in my work here. So I'm going to keep the coefficient in the front, 0.839. But instead of T2, I'm going to say that T2 is 1.774 T1. So I can see, as you can see here in this line now, the only variable that's unknown is T1, right? So just multiply both these terms on the left and then just do a little algebra. So if you take your calculator and you punch in 0.839 times 1.774, you'll get a coefficient of about 1.488 T1. Nothing has changed on the right side, but as you can see, the left side has the T1, the right side has the T1. So this is where you combine like terms by doing correct algebra. So I'm just going to subtract 0.259 T1 on both sides, and if you do that correctly on the left side, you'll get 1.229 T1, which is equal to 411.6. And then to find T1, divide both sides by the coefficient of 1.229 here. That's it. Okay, so T1, if you punch in correctly on your calculator, should come out to be about 334.91 newtons, and that roughly matches choice D, okay, which is about 335. Okay, all right, that's it. I hope that helps for this particular video. Stay nerdy, don't be whack.